This is your presenter, Asloob Mudassar, and I am presenting slide number 18H of the course on atomic and molecular physics. In the today's lecture, I shall be covering the following topics: centrifugal distortion, influence of electron motion, vibration of diatomic molecules. So you see that previously I have delivered lecture as 18A, 18B, 18C, 18D, 18E, 18F, 18G. So this is the 2 days lecture. If you want to understand the 2 days lecture, you must go through the previous lectures I just mentioned, because this is in continuation of these lectures. Centrifugal distortion. Now we are going to include the centrifugal distortion and its effect during the rotation of a real molecule. Now you see that now we are talking about the rotation of a molecule. Before that we have ignored the rotation. During the rotation of a real molecule, centrifugal force acts on atoms, and the internuclear distance widens to a value r. The centrifugal force is compensated by the restoring force, which holds the two atoms together. The two forces are given below. So the first one in equation number 131 is the centrifugal force, given by Fc is equal to m omega square r. And the second one is the restoring force. Fr is equal to minus the derivative of the potential energy with respect to r, and then multiplied by the unit vector r to give you the direction of the restoring force. So these are the two forces. Around Re, Re is, you know, that the equilibrium separation between the atoms in a molecule. Around Re, the potential energy curve can be approximated by a parabolic function. That is the potential energy curve if you are concentrating on in a region around the value of Re, you can approximate the potential energy curve to be a parabolic function, which leads to a linear restoring force. So you see that if you assume that potential energy E pot is of the type of a parabolic function, putting that function over here, and if you differentiate that one, you will get the restoring force Fr to be equal to minus K into R minus Re multiplied by the unit vector R hat. Now equating equation number 131 and 133 and introducing the value J is equal to I omega, or J square is equal to I square omega square, and putting the value of I over here, it becomes J square is equal to I square omega square is equal to M square R4 into omega square. So one gets this value. Equate the two equations and then introduce J square. And you know that J square can also be written as J into J plus 1 into H bar square, because J will be treated as the total quantum number of the molecule, and it will have its magnitude, which will be equal to J into J plus 1 multiplied by H bar square. So putting this value over here, on one side you have the centrifugal force, on the other side, on the right hand side, you have the restoring force, and in between them you have the value of the J into J plus 1 multiplied by H bar square over mr cube, because you have introduced this value by introducing some value over here. That is, you multiply this one with m, that is you divide both sides, that is you divide by mr cube, and then also multiplied by mr cube in the numerator, and then introduce J square there. Then you will get this equation, this central equation, which is obtained from the equation on the left hand side. Now you see that if you solve this equation for the value of r, you will get r is equal to Re plus J into J plus 1 H bar square over mk into r cube. Now you see that from this equation, it is obvious that R is greater than Re, which means that their internuclear distance R is widened by the molecular rotation. So you see that when the molecule rotate, then from equation number 135, it is obvious that R becomes greater than the equilibrium separation between the molecules. So the distance, that is the internuclear separation between the two atoms of a molecule, will increase beyond the value of Re, and this is due to the motion, molecular motion, and this is due to the rotation of the molecule. So it means that the rotation of the molecule will widens the separation between the atoms of the molecules. In the last equation, for the right hand side, we approximate R is equal to Re, and the equation takes the following form. So you see that in the previous equation, if we assume that R is very close to Re, then you can replace R by Re, and then you will get this relationship, that is R is equal to Ra, and within the parentheses you have 1 plus j into j plus 1 h bar square divided by mk Re square Re4. So you see that you can put this also into this form, that is Re is equal to 1 plus x, where x is this value, that is j into j plus 1 multiplied by h bar square divided by mk into Re to the power 4. Now you see that this quantity, which I have regarded x, is much less than 1. We can take the square of both sides and then the reciprocal of both sides and the binomial series expansion, then give the following results. So what you do is that you take the square of both sides of equation number 136 and then take the reciprocal of that one and then expand 1 plus x, and then move 1 plus x in the numerator with a value of 1 plus x raised to the power minus 1, and then expand 1 plus x raised to the power minus 1 in the binomial series, and then you will get this relationship by putting the value of x back into the expression. That is 1 over r square will be equal to 1 over re to the re square, and then this expansion, the expansion of 1 plus x into the binomial series and putting back the value of x will give you 1 minus 2 times of j plus 1 into h bar square over m k r e to the power 4, and then plus 3 times j square plus j plus 1 whole square h to the power 4 divided by m square k square r e to the power 8 plus minus and so on. Rewriting equation number 125 for Re not equal to Re and replacing 1 over r square from equation number 137. Now you see that I have mentioned equation number 125 in the previous slide, in the previous lecture. So in equation number 125, if you assume that R is not equal to Re, then in that equation, when 1 over Re square appear, then you can replace the value of 1 over R square from equation number 137. So I am reproducing equation number 125, which is given in equation number 138. That is E rotational is equal to J into J plus 1 multiplied by H bar square divided by 2 times M into R square. So this is equation number 125. And I am now going to replace 1 over R square in this equation by the value of 1 over R square from equation number 137. And you will obtain equation number 139. For a given J, the centrifugal widening makes the moment of inertia larger and the rotational energy smaller. This effect overcompensates for the increase in potential energy. You know that the moment of inertia is I is equal to mr square or mre square in this particular case, for example. And for a given j, for example, you are provided a value of j, then for a given j the centrifugal widening, and you know that I have already discussed that during the molecular rotation the widening of the molecule takes place, and during the centrifugal widening makes the moment of inertia larger, because the moment of inertia is given by I is equal to mre square. So you see that the value of r will increase beyond the value of ra, so it means that the moment of inertia becomes larger and the rotational energy becomes smaller, because the rotational energy contains a moment of inertia in the denominator. So when the denominator becomes larger, then of course the rotational energy becomes smaller. This effect overcompensates for the increase in potential energy. So you see that here the potential energy, if the potential energy increases, then you see that this will be compensated by the decrease in the rotational energy because of the increase in the moment of inertia due to the rotation of the molecule and due to the effect of centrifugal widening. Now you see that this is the diagram which shows you the compensation of the centrifugal and the restoring force in the non-rigid rotating molecule. So you see that this is a non-rigid rotating molecule. The curve for the potential curve for this one in the approximation that we are considering a small region about the value of Ra, that is a parabolic is constructed. So E potential of R is representing the shape of a parabola in the region in the small region around the value of Ra, and the compensation of the centrifugal and the restoring force in the non-rigid molecule shows at any point you see that the centrifugal force Fc is compensated by the restoring force Fr, which are shown respectively with the red arrow and green arrow respectively. At a general point on the potential energy curve, these two will compensate each other. And you see that this compensation is what I have described in the previous paragraph, that is in this paragraph. That is, for a given value of J, the centrifugal widening makes the moment of energy larger and the rotational energy smaller. This effect overcompensates the increase in potential energy. Introducing the following rotational constants, Be is equal to h bar over 4 pi c m into Re to the power 2, and then De is equal to h bar cube divided by 4 pi c k m square Re to the power 6, and then He is equal to 3 h to the h bar to the power 5 divided by 4 pi c k square m to the power 3 and Re to the power 10. These are the three constants that I am going to introduce in the expansion that I have shown over here. That is in this expansion. And now at the same time, I am also introducing a quantity F rotational as a function of J. So F rotational as a function of J, you know that I have already discussed an expression for the F rotational of J. And this is what you can find out from the previous lecture, that F of rotational along with the expansion that I have given and defined in the previous one or two pages. So F rotational of J is equal to Be as a function of J into J plus 1 minus De into J square and J plus 1 squared plus He into J cube into J plus 1 cube minus and so on. So you see that here in the expansion, I have introduced the constant Be, the constant De, the constant He defined in equation number 140, 141 and 142 respectively. The higher order constant He, you see that if you consider the three terms in this expansion, then He will be the higher order constant. The higher order constant He must also be taken into account when fitting the spectroscopic data. So you see that sometimes we want to find out or want to measure numerically the values of the constants Be, De, and He, and then you need to consider the constant He also in order to fit this data, this curve into this spectroscopic data, so that you can determine the unknown constants. Now let's discuss the influence of electron motion. Influence of electron motion. What is the effect of electron motion on the rotation of molecules? This is what we are going to determine, and we are going to answer this question. That is, what is the effect of electron motion on the rotation of molecules? In the axial symmetric electrostatic field of the two nuclei in the non-rotating molecule, the electrons precess around the space-fixed molecular z-axis. This is what we have already determined in one of the previous lecture of the series. The average projection, which is independent of capital R, of the angular momentum of the electron shell. You know that the angular momentum of the electron is represented by capital L, and it could be a function of R, which is the internuclear separation between the two atomic between the two atoms in a molecule, which is also given by the which is also given if more than one electrons are involved, then this is given by the vectorial sum of the individual angular momentum of the individual electrons, and each of these Li will be proportional to the value of will be proportional to the capital R, will be a function of capital R, where Li stands for the angular momentum of the ith electron. So this capital R, you know that it depends upon capital R is constant. The average projection of the angular momentum of the electron is constant. And the angular projection of capital L on the z-axis is given by the average value of Lz, which is equal to lambda times h bar. This is capital lambda times h bar. So the projection of capital L onto the z-axis will be represented by capital lambda times h bar. The projection is simply h is lambda, capital lambda, and we multiply it with h bar to give you the dimensions of the angular momentum. And on the left hand side we have the average value of the z component of the angular momentum. The molecular states with the electron spin s not equal to 0. So you see that here we are considering the molecular states in which the spin of the electrons, the total spin of the electron is not 0 in atoms with weak spin orbit coupling. And you know that if s is not equal to 0, and in addition to that one, if the spin orbit coupling is weak, that is s and L are not coupling together, the spin capital S precesses independently about the z-axis with a projection given by ms. So capital MS is actually the projection of the spin angular momentum on the z-axis, the average of which one is written on the left hand side. That is the average of SZ value is equal to capital MS multiplied by H bar, where capital MS is the projection of the total spin capital S on the z-axis. And the average value has been written in equation number 145. And you see that in this equation, while writing equation number 144 and 145, we have assumed that there is a weak coupling between the spin and orbit. That is, the spin orbit coupling can be neglected. And we have written these two equations in which we are assuming that the angular momentum of the electron and the total spin of the electron will precess independently about the z-axis. Both the projections will add to give you capital omega times h bar is equal to capital lambda plus capital S, and these two are multiplied by h bar. This is what I shall show equation number 146 in graphical form in the next slide. So you see that the total projection due to capital L and capital S will be equal to capital omega. Under strong spin orbit coupling, L and S couple to form capital J, and capital J will be equal to capital L plus capital S, and the projection of the capital J, because if L and S couple together to form a total J of the molecular system, then this capital J, you know, that will precess about the z-axis, and the projection of that one on the z-axis represented by the average value of JZEL will be equal to omega times h bar, where EL may corresponds to the electronic system or the electrons that we have considered in a molecule. So the average value of the Z component of the angular momentum or the projection of the total angular momentum J on the z-axis, the average value of which is average of Jz to the power El is equal to omega times h bar. And this capital omega is what I have defined in equation number 146. Now you see that I am going to show you graphically the representation of these quantities. Now you see that in this figure, which is the part A of this figure, I have shown two atoms A and B, or two nuclei A and B. They are separated by a distance capital R. And I have shown the total angular momentum L of the electron, capital L. And you know that the capital L will carry out a precessional motion in a loop shown with a dotted black circle. The L will carry out a precessional motion about the z-axis. And the average value of L, the projection of that one on the z-axis will be capital lambda times h bar. And here I am assuming that capital S is equal to 0, that is the total spin of the system is 0. And this capital N is actually the nuclear angular momentum. So capital N is the nuclear angular momentum, capital L is the electronic angular momentum, and these two quantities will add together to give you the total angular momentum J of the atom. So let me read the corresponding paragraph over here. Capital J of the rotating molecule. Of course, since you know that we are considering the rotation in this current lecture, so J of the rotating molecule is now composed of the angular momentum N of the molecular motion. So you see that when molecule carries out its motion, then of course the angular momentum capital N is constructed, or the capital N can be associated with the molecular motion. And the projection lambda h bar or the omega h bar for capital omega is not equal to 0, the total angular momentum J of the molecule is no longer perpendicular to the z-axis, which you can see in this figure. That is, since capital lambda is not equal to 0, or consequently the capital omega is not equal to 0, so you can see over here in this figure that the capital J will also be not perpendicular to the z-axis, but it is inclined at some angle, because capital J is actually the vectorial sum of the nuclear angular momentum capital N and the orbital angular momentum of the electrons capital S. Because in this figure we are assuming that the total spin of the electrons is 0. Now we consider the next figure in which the total spin of the electrons is not 0. So capital S is not equal to 0. So you see that capital S will carry out its precessional motion about the red loop, about the dotted red loop shown over here, and its projection on the z axis is capital sigma times h bar. Similarly, the angular momentum L of the electron will carry out a precessional motion in the blue dotted loop, and its projection on the z-axis is capital lambda times h bar. And you know that N I have defined earlier, N is the angular momentum of the nucleus of the molecule. So capital J and capital L will combine with capital N to give you capital J of the system. And the projection of capital J on the z-axis will be capital omega times h bar. So let me read the corresponding text. Since the total angular momentum of a free molecule without external field is constant in time, the molecule rotates around the space fixed direction of J. The molecule rotates around the space fixed direction of J. Consider this sentence, that the molecule rotates around the space fixed direction of J, and for capital lambda not equal to 0, the rotational axis is no longer perpendicular to the molecular z-axis. So the rotation of the molecule will take place about the J direction. Angular momentum of the rotating molecule, including the electronic contribution, is shown in these two diagrams. In the first diagram, the capital S, that is the total spin, was equal to 0. And in the following diagram, in the lower diagram on the part B, the total spin is not equal to 0. And both the spin and this is the case of weak orbital spin orbital interaction, in which capital S and capital L rotate independently, and then they will add together with the with the angular momentum of the nucleus of the molecule n, and then together they will form the total angular momentum J of the molecule. So the molecule will then rotate about a space fixed direction of J, provided this capital lambda is not equal to 0. In the symmetric top model, the whole electron shell is regarded as the rigid charge distribution. In the symmetric top model, the whole electron shell is regarded as the rigid charge distribution that rotates about the z-axis. The rotating molecules as symmetric top The rotating molecules as symmetric top have two different moments of inertia. I1 of the electron shells rotating about the z-axis, and I2 of the molecule. And when we talk about the molecule, it means that I2, that of the nuclei plus the electron, rotating about an axis perpendicular to the z-axis. Because when the molecule is rotating about an axis perpendicular to the z-axis, then of course we shall talk about the symmetric top model. And in that model, the value of moment of inertia I2 is much greater than the moment of inertia I1, where the moment of inertia I1 is that of the electron shell rotating about the z-axis, and I2 is the moment of inertia of the molecule. The rotational energy of the symmetric top is given by E rotational is equal to jx square divided by 2ix plus jy square divided by 2iy plus jz square divided by 2iz. So you see that due to the symmetry, we are here setting ix is equal to iy. And then this ix is equal to iy is equal to I2 is the moment of inertia of the molecule. Whereas I1 is equal to, whereas Iz is equal to I1, that is that of the electrons. This is the moment of inertia of the electrons, because the electrons are carrying out its motion about the z-axis. And of course, I1 is not equal to I2. So from the previous figure, you know that the square of the z component of J is equal to omega square times h bar. That is, you can take the square of this quantity, that is Jz, where Jz is actually the z component of the angular momentum. For example, this quantity, take the square of both sides of this equation, which I am introducing over here, and I am using this quantity. So you have J z square is equal to omega square into h bar square. You know that capital J square, which is the total angular momentum, can be expressed in its component form as j square is equal to jx square plus jy square plus jz square. And I have moved jz square on the right hand side. Now you can put the value of j square. The value of j square is equal to j into j plus 1 times h bar square, and the value of jz square is equal to omega square times h bar square. So this whole quantity, that is j into j plus 1 minus omega square, this whole quantity multiplied by h bars, can be written as n square h bar, where n is the angular momentum of the molecule. Because on the left hand side we have jx square plus jy square, which is of course the angular momentum of the molecule. And on the right hand side, you know that we have defined this value to be equal to n square times h bar square, where n square is equal to j into j plus 1 minus omega square. So inserting this equation into equation number 148, and you know that this is equation number 148, and using the term value f of j is equal to rotational energy of the molecule as a function of j divided by hc of the rotational levels. So f of j can now be written as f of j j and omega, that is f is a function of j and omega. This is equal to be times j into j plus 1 minus omega square plus a times omega square. And you know that this is what we have introduced in the expression of f of j is equal to e rotational of j over hc, and E rotational has been defined in equation number 148. So using equation number 148 and using the value of jx square plus jy square is equal to n square into h bar square, I have introduced I have written f of j omega to be equal to pe times of j into j plus 1 minus omega square plus a times omega square. Where the constants a and b, be has already been defined, and the constant a is now going to be defined below in equation number 153. So where the rotational constants are related by a is equal to h bar over 4 pi c I1, which is much greater than be, which is equal to h bar over 4 pi c L2. Because I1 is much smaller than I2, on this basis the constant a is much greater than be. A omega square is constant for all rotational levels of a given electronic state with quantum number omega. The term being independent of J is added to the electronic energy Te of the molecular state. The term therefore is therefore not influenced by the centrifugal distortion. So let me read again this paragraph. A omega square is constant for all rotational levels of a given electronic state with quantum number omega. The term being independent of J, that is this term A omega square being independent of J, is added to the electronic energy Te of the molecular state. And you know that Te is the kinetic energy or the electronic energy of the molecular state. The term therefore not influenced by the centrifugal distortion. And you know that in the centrifugal distortion, the parameters that appear will not appear when we will add A omega square, which is constant for all rotational levels and is added to the electronic energy Te of the molecular state. The ground states of a majority of diatomic molecules are written as 1 sigma states with capital lambda and capital omega is equal to 0. For these states, equation number 152 is identical to equation number 128. So I cannot show equation number 152 because it was referenced from the previous lecture. So the ground state will mainly be written as 1 sigma state with the capital lambda capital omega is equal to 0. Under that condition, the ground state will be 1 sigma. Vibrations of diatomic molecules. For non-rotating molecule, that is if the molecules are not rotating, then J is equal to 0 is set in equation number 121. Around R is equal to RE, E potential can be approximated by a parabola. If RE is equal to 0 and using omega is equal to square root of KR divided by capital M, then we can write the E potential is equal to half of Kr into R minus Re is equal to half kr into r square is equal to half omega square m into r square. So you see that this is the potential function that we are approximating this potential by the value of the parabolic form, and we have written these quantities. Inserting equation number 121, replacing capital S by psi of vibration to be equal to R into S of R, one gets the following quantity. So you see that in equation number 121, which is mentioned in the previous lecture, in that there was a differential equation. In that differential equation, we have replaced the wave function psi vibration to be equal to R times S of R. Then one gets that differential equation to be modified as given in equation number 155. So d square psi vibration divided by dr square plus 2m over h bar square, and within parenthesis e minus half omega square m, and outside this parenthesis we have psi of vibration is equal to 0. So you see that this is the differential equation where psi b is actually the wave function corresponding to the vibrations of the molecule. The solutions y vibration, y psi yb, that is psi vibration, are the vibrational wave functions. The solution is the product of the exponential function and a Hermite polynomial. So you see that if you find out the solution of this equation, you will notice that psi yib, that is the vibrational wave function, will consist of the product of the exponential function and the Hermite polynomial. So psi yib as a function of r is equal to e to the power minus m omega divided by h bar square, and this whole term is multiplied by r square, and then the Hermite polynomial has hv as a function of r, where v is the vibrational quantum number. For a parabolic potential, the vibrating molecule is a harmonic oscillator, and the vibrational energy levels are quantized. So you see that in the harmonic oscillator, the vibration levels are quantized, and the space between the vibration levels will also be fixed. The energy levels of the harmonic oscillator are now given by, this is the eigen energy state that can be obtained by the solution of the previous differential equation. So E of nu will become equal to parenthesis containing nu plus half, and outside that one we have h bar omega, and where the values of nu where the values of v are, where v is the vibrational quantum number, or v is equal to 0, 1, 2, 3, and so on. That is, the lowest value of V is equal to 0, not 1. The energy levels are equally spaced. That is, the delta E will be equal to h bar omega. And h bar and delta E is actually the energy separation between the two consecutive vibrational level, which is constant and which is equal to h bar times omega. So you see that omega is written as omega is equal to square root of kr over capital M. And kr is equal to d square E pot divided by dr square, evaluated at a value of r is equal to Re, where Re is the equilibrium separation. And you know that if you put the value of V is equal to 0 in equation number 157, you will get the lowest vibrational energy to be equal to E is equal to half h bar omega. The parabolic potential of diatomic molecule at R is equal to Re deviates more and more for larger value of absolute value of R minus Re, and can be approximated by the Morse potential described below. So you see that Morse potential is the very important and very famous potential, which I am mentioning for the first time in this course on molecular physics. So E potential as a function of R is equal to EB times the square of 1 minus e to the power minus a times r minus re. So you see that all the parameters are known except A, where A is some constant, and EB is the binding energy of the molecule, and E pot is the potential energy as a function of R. So this is the Morse potential. So you see that while before writing the Morse potential, I mentioned that the parabolic potential of the diatomic molecule at R is equal to Re deviates more and more for larger R minus Re mod value and can be approximated by the Morse potential. So you see that this deviation from the value of Re is well described by the Morse potential. Using Morse potential into the radial part of the Schrodinger equation given in equation number 121, which gives exact analytical solution. So you see that this important and this most important value of this Morse potential is that when it is used in the Schrodinger wave equation, you will get an exact analytical solution. And the energy eigenvalues and the energy separations are given by. So this is the energy eigenvalue. That is E vibrational as a function of vibrational quantum number V is equal to h bar omega naught multiplied by nu by V plus half, and then the second term is minus h bar square omega naught square over 4 ED, and it is multiplied by the square of V plus half, where delta E, that is the separation between the two consecutive vibrational level, is given by EVB at V plus 1 minus EVB at V. So evaluating VIB of V plus 1 from equation number 161 and also VIB and also E of VIB of V from equation number 161, you will get this equation shown in equation number 162. That is delta E as of that is the consecutive energy, vibrational energy between two consecutive level of the vibrational level is equal to h bar omega, and within the square bracket we have 1 minus h bar omega over 2 EB multiplied by V plus 1. EB is the binding energy of the rigid molecule. The vibrational levels are no longer equidistant. You see that in this case, notice that the vibrational levels are no longer equidistant, but the separations decrease with the increasing vibrational quantum number V. So as you go higher along the vibrational curve with the energy, you will notice that the separation between the vibrational levels will decrease with the increase in vibrational quantum number V. The term values TV, which is equal to EV over HC, are given by. So the term values for the vibrational levels, which is T vibration as a function of V, is equal to omega E times V plus half minus omega E XE times the square of V plus half, where omega E and XE are defined on the next page. The vibrational constants and the vibrational frequencies are given by omega V is equal to omega naught over 2 pi c. Omega V XE is equal to h bar omega naught square divided by 8 pi c into EB, which is equal to omega E square multiplied by HC over 4 times EB, and omega naught is equal to alpha is equal to 8 times the square root of 2 times EB over capital M. Omega naught is the frequency of a classical oscillator with a restoring force constant Kr is equal to 2a square EB. Kr is measured from the centrifugal distortion of rotational levels, and the measurement of EB can be used to determine the Morse potential constant A. More general expansion of the potential is represented as given. So you see that E potential as a function of R is equal to summation over n, and the term is 1 over n factorial multiplied by the nth partial derivative of E pot with respect to R and evaluated at a value of R is equal to RE multiplied by the nth power of R minus RE. With this potential, Schrodinger equation can only be solved numerically. Now you see that analytical solution is not possible and only numerical solution is available. Later it will be shown that the real potential can be very accurately determined from the measured term values of the rotational and vibrational levels. So you see that we shall be able to extract the real potential from the measurement of the rotational and vibrational levels. The separation between the vibrational levels decreases with increasing V, and the separation stays finite up to the dissociation energy. A finite number of vibrational levels fit into the potential well of a bound molecular state. Electronic states in an atom are infinite in number, and the separation between the Rydberg levels converges to zero when R approaches infinity. The experimental dissociation energy, which is ED, and on the superscript we have written EXP to stand for the experimental. So the experimental dissociation energy EXP is the energy where the molecule is dissociated from its lowest vibrational level. The binding energy EB of the potential well is measured from the minimum of the potential. You know that these are the two quantities that I have mentioned graphically in one of the potential energy curves in the previous lecture. So in the previous lecture, you can also notice that I have defined ED, that is the experimental dissociation energy obtained experimentally, which starts from the lowest vibrational level, and also the binding energy, which starts from the minimum of the potential. So the difference between them is really very small, and the difference between them is equal to the half is equal to the minimum energy, minimum vibrational energy, which is given below. That is ED experimental is equal to the vibrational energy, the binding energy minus half H bar omega. So you see that these two quantities are related through the potential through the minimum binding and through the minimum vibrational energy of the molecule, which is equal to half H bar omega. And this is what I have illustrated in one of the graphs of the potential curve. There I mentioned what is ED and what is EB. You can consult that graph in the previous lecture. So this is the end of slide number 18H. The lecture is still continued.